Okay, so good afternoon, dear listeners to the Non-Associative Algebra seminar. Today is July 17, and we have Alexey Petukhov from the Institute of Transmission Problems from Moscow, Russia, and he's going to talk on Witt Lie algebra and the associative primitive ideals. Please.
Thanks for the invitation of the seminar. Well, let's proceed with the subject of my talk. So, first of all, I would like to start with some preliminaries. So I would like to consider a Lie algebra G and its universal enveloping algebra.
Sorry, we cannot hear you.
Sorry. So let's
Okay.
just thanks for the invitation on the seminar. I would like to start my talk. So first of all, I would like to provide some very preliminary stuff. So I would like to start from a Lie algebra G and consider its universal enveloping algebra, which is some version of non-commutative polynomials on G star, together with the Poisson algebra of G, which is a fancy way to talk about the symmetric algebra of G. Well, I would like to study two-sided ideals of UG and Poisson ideals of SG. And well, for two-sided ideal, they will be automatically a joint action stable. And well, the Poisson ideals are exactly the ideals of SG, which are a joint action stable. And the joint action, well, it just comes from the action of G, of Lie algebra G on itself, and then it just extends to the action on SG. And well, it might be not the most canonical way to do it, but it should be a good one. Next, an ideal I of UG is called primitive if it is the annihilator of a simple UG model. And an ideal of SG is primitive if it is the maximal Poisson ideal inside the maximal ideal of SG. So it might be so that these definitions are not very familiar one to each other, but it's easy to check that the annihilator of a simple, just a simple module is by definition a maximal, well, say a left simple module is by definition a maximal, it can be identified with the maximal left ideal, and then its annihilator is the maximal two-sided ideal inside this maximal left ideal. And from this point of view, first definition and the second one looks a bit familiar. And well, it's easy to check that in the case of algebraic Lie algebra, primitive ideals stand for the orbits for the cojoint action. And for UG, well, primitive ideals are something like orbits in the respective orbit space. And let's see how it works further. So maximal ideals of SG can be identified with G star, and primitive ideals of UG can be identified with something else. And the general idea behind what is going on here is the Kirillov orbit method. And let me describe in details. Well, let me say a few words about this gadget. And from the point of view of general algebra, the primitive ideals of UG provide some control on the two-sided ideals of UG, and primitive Poisson ideals of SG provide some control on the Poisson ideals of SG, in the sense that, well, radical primitive ideal stands for the a joint action stable invariant subvarieties of G star, and every single such subvariety is just a union of several orbits. And that should be clear enough. And then this some kind of control. At least you have to know what you need to start with to construct all such varieties. And another good idea here might be that the ideals of, well, and anyway, it all the statements are some versions of Hilbert-Nullstellensatz. And another good analogy here is that the radical ideals of C of xy, they are sort of controlled by points of C2, and radical ideals can be identified with subvarieties of C2, and every such subvariety is a union of several points. And, well, the story with primitive ideals and the two-sided ideals and radical two-sided ideals of UG is very similar. So, fortunately, it's known that under some assumptions, there is a bijection between primitive ideals of UG and primitive ideals of the symmetric algebra. And, well, whenever it works, it usually extends this bijection not only between primitive ideals, but between radical ideals on both sides. It's very well, Kirillov himself, with some minor modifications from other persons, say, I think, well, Kirillov established this bijection between primitive ideals and this bijection between radical ideals on both sides. I think that it's done by Mathieu for finite dimensional nilpotent Lie algebras. And up to some extent, this method can be extended to semi-simple Lie algebras. The primitive ideals are known here. They use some sort of Vermes constructions to classify anything, and all the Verma models and similar models, they are induced by some analogy of the Kirillov-Sorbis method, and they are a little bit familiar, but with the story with finite dimensional nilpotent Lie algebras, and then you can glue up all the story with nilpotent Lie algebras, solvable Lie algebras, and semi-simple Lie algebras all together to get some classification of primitive ideals for universal development algebras of all finite dimensional Lie algebras. Well, this is the story for characteristic 0. For characteristic P, it's a bit different, but still a little bit familiar. So my idea was that it really works up to some extent for non-finite dimensional algebras as well. It might be not a very deep one, but it seems that it was ignored for quite a long, and it was believed that the primitive ideals for universal development algebras of infinite dimensional algebras, it should be very wide, and it should be very hard to study them. And they claim that from some viewpoint, they can be even simpler from time to time. Then it can be simpler to describe them than to describe the primitive ideal for finite dimensional algebras. And let's see how it works. So I have a work about limits of infinite dimensional limits of nilpotent Lie algebras, a joint work with Mikhail Ignatiev, where we establish exactly this bijection between primitive ideals for SG and primitive ideals of UG. There is a series of work with Ivan Penkov, which is based on works of Baranov, Zhilinsky, and Zalewski, about non-finite dimensional limits of simple algebras, where we also achieved some very reasonable answer. And I claim that in general, it's simpler than the answer available for finite dimensional algebras. We have some good progress, at least on the level of primitive ideals of Poisson Lie algebras for Witt Lie algebra and Virasoro Lie algebra, with some major contribution by work of Susan Sierra and Natalia Yudu. There is some activity in this direction provided by Susan Sierra and I forgot the name, Rekha Bishwal, where they shown that, well, something reasonable in this problem was shown here about the finite dimensionality of every non-trivial quotient for a fine Lie algebras and loop algebras, and we have some idea with Susan about all this subject, how to really provide some classification of primitive ideal here, at least on the Poisson side. We have to think harder to achieve anything for for UG side. Well, we'll see what will happen in future. And they claim that I believe that for every infinite dimensional algebra, one can achieve some very similar results, of course, for different Lie algebras, or even some deformations, something like that, some quantum algebras, or whatever. It should be, well, the respective classification of primitive ideals should be available and should not be very hard, and it should be up, in some sense, simpler than the classification available for finite dimensional algebras. But, well, I can't do everything in finite time, and I welcome everyone who would like to think about the subject more to just do some works in direction of other algebras. Okay, so now let's just talk more about primitive about Virasoro Lie algebra, Witt Lie algebra, and all the related stuff. So for well, let's start from the basic definition. So Witt Lie algebra is just the Lie algebra of vector fields of the form c of x plus minus dx. So they are just polynomials with x minus 1 added to them, and then just vector fields. And Virasoro Lie algebra is the only one-dimensional extension of the Witt algebra. And I would like to denote the central part which we extend, by which we extend our Witt Lie algebra by z, and the respective space by cz. And there is a standard formula for the cocycle of the respective action, but I mean, I don't really need it much. It's enough to know to me that such a formula exists, and up to some automorphisms and similar things, it's unique. So now we're ready to talk about some results in this direction. Theorem A. So what is the point of the stuff? So I would like to talk about Poisson ideals of the respective symmetric algebra, and the primitive Poisson ideals of the respective symmetric algebras, and next about radical Poisson ideals. And, well, to define the primitive ideal of the respective Poisson algebra, I have to first describe all the maximal ideals, and the maximal ideals of G, they can be identified with the points of G star, at least under the assumption that my main field is uncountable, for example, C. And then just, well, all the maximal ideals, they can be identified with the full dual space of W, and then we attach to every such an element lambda from W star some maximal ideal, and we really will be a bit more interested in maximal ideal, but it's easier to parameterize them by the elements of W star. And then, but we consider the maximal Poisson ideal inside this M lambda, and we denote the result by I lambda. So, and the formal description of primitive ideals in the respective symmetric algebra of Witt algebra is that they are ideals I lambda for different lambdas. And, well, the next very natural step is to explain when these ideals are the same, and even simpler question is when these ideals are non-zero. So it's very clear that every ideal contains zero ideal, which is Poisson ideal, and maybe it happens so that for most lambdas, I lambda is really zero. And, well, the result is here. So I lambda is non-zero if lambda satisfies one of the equivalent condition 1 or 2. So the dimension of the analog of the tangent space to this orbit at lambda must be finite dimensional. Or it should be so that when we evaluate lambda on some ideal of our ring C of x plus minus 1, x plus minus, multiplied by dx, the result should be zero on all this subspace of finite codimension. And well, we have some nice class of such finite dimension. Well, we have some nice class of linear functions, and we use it for this nice class of functions. We have this property that I lambda is non-zero, and well, we decided to provide some name to this class, and we call such function lambda local. It's clear. It's easy to check that such local functions, they are they form a subspace of W star, and also they even form a submodule of W star. So even if we consider from start the full dual space of W star, it turns out that we really need only some small part of local functions, and we can ignore the rest. Okay. Well, we have a theorem about primitive ideals of Witt algebra, and next we would like to deal with Virasoro algebra, and for Virasoro algebra the result really reduces to the result for Witt algebra. So first of all, assume that I lambda is non-zero for some linear function lambda from the dual space of Virasoro Lie algebra, then this function must be zero. Well, just we have, well, it's very clear that such an ideal will always contain the element z minus lambda of z. And it can be so that this ideal is equal to the ideal generated by z minus lambda z, or is different. And this ideal is really different if and only if lambda of z equals to 0, and the restriction to lambda, well, and the push forward of this lambda to w, when we just send z to 0, is really a local function. So the result for Virasoro Lie algebra reduces to the result of about Witt algebra. Well, all this stuff about finite dimensionality and the description of local function, it was enhanced by Susan Sierra and Natalia Yudo to the result about finite Gelfand-Kirillov dimension, and the real part which stands for the finite Gelfand dimension here is the equivalent condition 1 from theorem A. That is that the tangent space to our orbit is of finite dimension, and it turns out that, at least in this case, the statement is equivalent to the statement that their corresponding variety is a finite GK. And in general, these notions should be very close one to each other, but I don't. Well, there is a clear implication in one direction, and I'm not sure how to achieve such an application in the other one. But anyway, just in this case, they are the same. And in general case, the story can be a bit complicated, but at least for reasonable algebras, it should be reasonable. So, and well, the statement by the theorem by Susan Sierra and Natalia Yudo is that every non-trivial quotient of the symmetric algebra, Virasoro algebra, and Witt algebra is a finite GK, and a similar statement for affine algebras was achieved by Susan Sierra and Rekha Bishwal. Well, now we know when our ideals are, well, at least primitive ideals are 0 or non-zero. And let's try to understand when two such ideals are the same. The story is as follows. Well, and to deal with this question, we need first to discuss in detail some properties of local functions, some notions which arise in a natural way when we try to talk about them. So let's do it. So the following conditions are equivalent. So all these conditions really means that our lambda is a local function on the full dual space to Witt algebra and Virasoro algebra. The first one is really the one which shows up in theorem A, part 2. The second one, well, just assume that we have a linear function on C of x plus minus, then we can pick some bases here. For example, we can just pick monomials and evaluate our linear function on this basis. And, well, this linear function is uniquely defined by its values on the basis. And it turns out that our linear function is local. So this means that condition 1 is satisfied if and only if the respective sequence is linearly recursive. And it's easy to study and do whatever you want with this linearly recursive stuff. And it's also clear that, say, sum or product of two such sequences is also a sequence of the same form. That's a good way to think about local functions. Another good way to think about them is to say that, well, let's assume that we have some gadget which evaluates, which picks a vector field q of x dx and send it and evaluates some derivatives of this vector field, and then plug inside values at some points and sum the result up with some coefficients. And it turns out, and it's easy to deduce, and this really can be easily deduced from condition 2 because we knew everything about linearly recursive function, as that the condition 2 is satisfied if only if lambda can be presented as a sum of this derivatives, evaluation of derivatives at some points, and some coefficients. And the last way to think about it is really related to 3, and it's more like 3 stars than fair 4. That is, well, such a local function can be thought of just as some gadget which pick a vector field and then collects local information at a few points. Local means that we need to know some derivatives at these points, and then we just glue it together by some linear function, and that's it. So somehow our local function is a gadget which exists on C star, or which is an analog of a complex circle. Well, the list of such points, coefficients, derivatives, whatever, can be chosen in a unique way. And we call the list of points in which our function is supported, well, the support of this function. So everything interesting for a linear function happens only in a finite collection of points. And just we would like to consider and talk more about these points. Now we're ready to state theorem C, which really explains when two different linear local functions defines the same primitive ideal. So I really consider two linear local functions, lambda and mu, and assume that both have some support. Next, what I do, I can say that, well, on the previous slide, we have the sum, and we can, for every given value lambda, we can consider the piece of the sum which is attached to this value alpha. It can be so that we evaluate several different derivatives at the same point, and I denote by d of I the derivatives, the maximal derivative evaluated at the point alpha I, and I repeat this procedure for every I. And then just, well, what I get out of this procedure is that for every given point I get some number, and I have a finite collection of points. I would like to just plug the result in some single gadget, and it's very natural to call this gadget partition, just as a collection of numbers, and I assume that they are, say, non-increasing, and of course it's finite. And I denote this partition d of lambda. So to every local function, I can attach a partition. And moreover, I can really attach some number to each odd part of this partition. And the real essence of this number is that, well, we have the maximal derivative which we consider in a given point, and we should consider some coefficient which is associated to the derivative in the middle degree. And if there is no middle degree because of some even odd game, well, we just have no additional numbers and have, well, that's how it works. So we attach to some part, to all odd parts some number. And then, well, now when we have all these gadgets with partitions, numbers attached to partitions, and so on, we're ready to explain when two primitive ideals are the same. And that is I lambda would be equal to I mu if the respective partitions are the same, and there exists the permutation of equal parts. Say just if we have some parts of size 3 for lambda and mu, we have, if the partitions are the same, then we have the same number of parts of size 3. And then it can be so that, for example, for the first, let it be 5 parts, we might have, say, numbers 5, 4, 3, 2, 1 attached to lambda, and then, say, numbers 1, 2, 3, 4, 5 attached to mu. And, if the multiset of these numbers are the same, or what another way to say it is to say that if we permute them by the action of multiplicative group, then one can be mapped to another, and this should be applied to every given to all parts of odd size. Then this partition will define the same primitive ideal, and if at least for one type of part we have that these multisets are different, then the resulting primitive ideals will be different. And these numbers, here I would like to mention that this number should be non-zero if we consider parts of size 1, and they should be 0, and they can be everything including 0 for all other odd integers, odd positive integers. This is just some formal theorem. Let me try to explain to you what does it mean. So the real essence of what is going on here is that we have this complex circle, and we have a few points here with some local data at all such points. Now we can act by Witt Lie algebra, and Witt Lie algebra is in some sense it is a Lie algebra of the group of diffeomorphism of the circle, or just C2, C1 without center, without 0 point. And then we can try to permute these points using the group of diffeomorphisms, and it's quite clear that, we can really map every collection of D points to every other collection of D points, but we need to do something with this local data. And what is going on with this local data? We can really apply here some local diffeomorphism at every such a point, and we really get some reasonable group which acts on all tensors at the given point. And the groups will be similar for different points, but of course, isomorphic and so on. And just we need to understand what the local group of diffeomorphisms can do to the tensors, and this parameter gives a rise from the description of the action of this group of diffeomorphisms, of local diffeomorphisms on tensors. And here, just that's how it works. I don't wish to give much more details about it. So the nature of this theorem is quite, it comes from the differential geometry, essentially. The proof is quite algebraic. We need to say this, that, just take care about these details or that details, but efficiently it is a statement about circle and the group of diffeomorphisms of circle. Okay, now I would like to show how to, just before I claimed that we can have some control over Poisson ideals, or what is more precise, we can have a control over radical Poisson ideals if I have the list of primitive Poisson ideals. And I would like to show how it works for the symmetric algebra of Witt algebra. So I need to introduce a little bit more notation. So let D be some partition, and we know by D star n the number of parts of size n and D. And then we did set space D to be the product of C star tensor, D star 1 copies of C star, D star 3 copies of C, D star 5 copies of C, and so on. Well, thanks to the fact that our partition is finite, it stands for some finite collection of points in which we store some differential geometric data. This space would be really some finite dimensional space, which is a product of fine lines and one-dimensional torsos. Well, now to each partition D and each subvariety L of space D, we attach a prime Poisson ideal. Efficiently, we just intersect all the primitive ideals, which stands for points of the space. And each prime Poisson ideal arises in this construction, or it arises from the augmentation ideal. And the ideals IDL and ID prime L prime are the same if and only if, well, the partitions are the same and L can be mapped to L prime by the action of the native symmetric group. Well, it just permutes, well, in every given block from the third line here, we can just permute elements of this block. And then if we can permute them all together using the action of this product of symmetric groups, well, this means that the ideals are the same. If not, then not. And that's our theorem about prime Poisson ideals here. I would like to say here that we can't explain, at least for now, we can't explain one such ideal is a sub-ideal of another ideal of this form. So when IDL is a subspace of ID prime L prime, but I think that it's not overcomplicated. We just need to think more about it. So now I'd like to proceed to the example for the ideals of cos GK dimension 2. In this case, and so we have the GK dimension of the respective symmetric algebra by the respective primitive ideal would be 0. Well, in our case, it would be always even. So just it will be 0 if lambda is equal to 0, and only in this case. And well, it should be at least 2 in all other cases. So 2 is the minimal non-zero number here, and so this quotient would be of GK2 if and only if our map lambda, which sends every element of our Witt algebra to numbers, looks as follows. So we should send our vector field qx dx to the value of this vector field of this polynomial q at some point alpha multiplied by some non-trivial constant plus constant multiplied by q prime of lambda. So we need to evaluate q of alpha and q prime of alpha and merge them together using some constants. And well, we have that two such primitive ideals are the same if and only if gamma is equal to gamma prime. This is some very special case about local functions which use only first derivative and zero derivative, so the value of function at the corresponding point, but at least the story here is very clear. And well, this finishes essentially the description of primitive ideals of cos GK2, and well, the respective orbit, it's clear how to imagine it. So we just how to imagine from the point of view of this idea as the circle and so on. So it just a collection of linear functions we just take, which just are defined as follows. So we pick some point alpha, then we just on the circle, and then we just evaluate the derivative of the polynomial corresponding to our vector field at this point alpha, and then just we should pick some constant beta and add the the value of the respective polynomial at this point alpha. But it turns out that this value beta doesn't affect everything, and when we act on this sort of differential geometric stuff by the group of diffeomorphisms, we can just send one such gadget to another one if and only if the coefficient behind q prime of alpha is the same for two such gadgets. Okay, so this is the story about primitive Poisson ideals. Now let's see whether or not it fits what we knew about the ideals in UG, where G is the Witt algebra. And well, there is a general concept of Kirillov's orbit method, which we mentioned before, and it really provides some recipe how one should construct a primitive ideal in UG out of the primitive ideal of SG. And the rule is as follows. So we need to pick our linear function. So pick some local function lambda of the form provided below. And then we need to consider some polarization for this linear form. The polarization means that, well, efficiently, every linear form lambda defines some symmetric form in our Lie algebra. So we need to just pick two elements from our Lie algebra, consider their commutator, and apply our linear function to this commutator. So this is defined by linear form. And well, it's very clear that it's skew-symmetric. And we need to consider some maximal isotropic subspace with respect to this bilinear form. And a polarization is polarization must satisfy two conditions. First of all, it must be a subspace. Second of all, it must be a maximal isotropic subspace with respect to this form. And the condition of being isotropic is written as written as lambda applied to the commutator of p equals to 0. So in our case, when we fix alpha, we can pick p, this polarization p, to be equal to all polynomials, all vector fields which have 0 at alpha. And that's written as polynomials of the form x minus alpha times every polynomial times dx. And the orbit method suggests that, well, we should attach to the primitive ideal of lambda the annihilator in the universal development algebra of Witt algebra of the induced module from P to W of the one-dimensional module of P defined by lambda. Lambda is a character of P, so it defines the one-dimensional module. Well, in short, it works. And the main trick here is that we really have a very good candidate for this induced modules. There is a work of students here on Chelsea Walton, where they have constructed a homomorphism from the universal development algebra of Witt algebra to some deformation of Weil algebra with a mild one. And efficiently, we was able to identify all these induced modules in the setting of this Weil algebra, just as some models of delta functions somewhere. And then when we knew just exact form of these models, it's easy to understand that their annihilator is really trivial, and then their annihilator would be equal to the annihilator of the map from our universal development algebra to this deformed versions of Weil algebra, and all these annihilators were studied in the work of Sierra and Walton, and just it really, and from all these considerations, it follows that the ideals constructed by Sierra and Walton are exactly the ideals which arise from this construction with polarizations and local functions and primitive Poisson ideals of GK2, and that's it. Thanks for your attention. If there are any questions or comments or whatever, I would be glad to discuss them or to answer them. Whatever.
Thank you very much. Questions, comments? Maybe in the chat. we have a question, but I think the author of the question is typing. It's not yet finished typing the question. Connections with Hopf algebras.
Of course, UV is the Hopf algebra, and I expect that something similar can be obtained for every infinitely generated Hopf algebra. But well, I dealt explicitly only with cases of UG for some finite list of finite dimensional infinite dimensional Lie algebras, like limits of nilpotent Lie algebras, limits of simple Lie algebras, Virasoro algebra, Virasoro algebra, Witt algebra, fine Lie algebras, loop algebras. Of course, there are more cases, there are more examples of Hopf algebras, but I mean, right now I have no works about it, but it might be a good plan for future.
Thank you for the the participant is asking to suggest some references.
There is a list of bibliography in them, and well, I assume that it provides some references.
Well, you have already shared your slides with us, so we will publish them on the website, so that everyone will be able to see the list of references. So I address the participant to our website, where we will publish this presentation, and he will be able to see the references. Thanks for sharing your slides with us. Any more questions? Well, so thank you very much for your talk. And thank you for the participations for everyone. And we will resume next week.